The standard normal distribution has mean 0 and standard deviation 1. Since every normal distribution we encounter has mean 0 and standard deviation 1, we can always use the standard normal distribution table. Or can we? Suppose we had a set of data values with mean mu and standard deviation sigma. We can normalize the set of data values by subtracting mu from each and then scaling the difference by a factor of sigma. Then our new values will be, this is referred to as the z-score of the data value. For example, suppose a sample of data has mean 27 and standard deviation 5. Find the z-score for a value of 23. We find suppose x has mean mu and standard deviation sigma. If z is the normalized value of x, what's the mean and standard deviation of z? We can find the expected value of z, and by the linearity of the expected value we get and so the mean of z is 0. We'll find the variance, which will be, and since the sigma is a constant factor, we could remove it as its square. And remember, subtracting a constant from a random variable leaves the variance unchanged. And so we get and so if x is normally distributed with mean mu and standard deviation sigma, then z will be a standard normal random variable. And this means we can use our table for any variable that's normally distributed. For example, suppose x is normally distributed with mean 27 and standard deviation 5. We'll find the probability that x is less than or equal to 30. So we'll find the z-score, that's x minus the mean divided by the standard deviation, which will be and so x equals 0 corresponds to z equals 0.6, and so the probability that x is less than or equal to 30 is the same as the probability that z is less than or equal to 0.6. This is the area to the left of z equals 0.6 under the standard normal distribution curve. And consulting our table, we find the area. Or let's consider another problem. So we'll find our z-score. So that's x minus the mean divided by the standard deviation. And so we find. Now, since our table of values only lists z-scores to 2 decimal places, there's no real point in keeping anything past those 2 digits. So we'll use z equals 0.91. The probability corresponds to the area to the right of z equals 0.91, which is complementary to the area to the left of 0.91. And so we find or let's consider IQ scores, which are normally distributed with a mean of 100 and a standard deviation of 15. What fraction of the population has an IQ of 80 or less? So we'll find our z-score for 80, which is and so that's the probability that z is less than negative 1.33. So we want the area to the left of negative 1.33. This is equal to the area to the right of 1.33, which is complementary to the area to the left of 1.33. And so we can use our table to find. And so that means about 9.18% of the population has IQ 80 or less. Or we could find the probability we fall in some interval. So for this, we'll need the z-scores of both endpoints. And so that's the probability that z is between these two numbers. So our probability corresponds to the region to the left of 0.67, from which we remove the region to the left of negative 1.33. So we can use our table to find the area of the region to the left of 0.67. The area to the left of z equals negative 1.33 is the same as the area to the right of z equals positive 1.33, which is complementary to the area of the region to the left. And so we have and so our probability will be